To the next one, we have here, what we want to do now is try to get some user input because we have, as you know, we have 20 plus examples and several more case studies that we can talk about, but we don't really know what it is. I mean, we've interacted with some of you, but there's several more that we don't quite know what it is that you want to use GeoFires for. And for this next session, we have about 40 minutes or so left. We created a little poll more about electricity. Great. We have a lot of case studies on electricity production with some of the building models. Definitely also super hot rock. We have some case studies there as well. Let's see, direct use heat, district heating, Monte Carlo simulations. I see some topics not as much of interest. That's good. We won't talk too much about that. Well, it seems electricity. I think that was actually the first ones we have ready. That may be a good one, and maybe other responses still come in. And again, we have more time in the afternoon session. We do have a hard stop at noon for the lunch break in 30 minutes. We're actually somebody needs this room here for during the lunch break. But let's just get started on electricity, and then we can see what's next, direct use heat, super hot, etc. So I'll take over the screen again. I'll share my screen again, and we did have electricity actually coming up first, so we did have some requests already in advance, and so we'll let's get started with that. Before though, I'll just dig right into it. Just want to highlight again a lot of the examples, and we may not get again to all of them, but they all can be found online and on the GitHub. So we highlighted first, there's a tab called examples, and different examples are listed there. So if we don't come to your particular example, that if it didn't win in the poll today, it is there. You can find all of that information as well. And all that links back to the folder examples, which is under the folder tests, which is on GitHub. You can find all the input decks there, which may be a good starting point for you for your case. And again, you can find the output deck as well, which is for the base case. So very, very quickly on the examples, we originally only had 6 examples, and we got feedback some time ago, we need more examples. And so I hope we addressed some of that as well. We have 20 plus examples at this point. But what we try to do with all the examples is not just target different applications, but also target different economic models, target different reservoir type models. That maybe was not something we had in the poll readily there as an option, but some of the different models, I'll highlight some of those other different types as well that you can choose from. So this is, I feel like, a little overview what we hope the different examples get to. And I'm going to be just focusing a little bit on the electricity here, maybe in the next 5 to 10 minutes or so. So, as I mentioned earlier, there was quite a lot of work that went into developing some of the correlations for the electricity end-use option. What GeoFires does not have is an advanced Aspen Plus type or type simulation where in real time it will simulate the heat exchangers, the compressor, pick the refrigerant, etc. It doesn't really do that. There have been talks about maybe we need that capability, and there are some modules even online you can find that do some of that, especially for ORC cycle. A lot of libraries or a lot of others have developed some capabilities there that, who knows, maybe we can link some of that. But right now, it relies on existing correlations that have been developed. Some of it that we find in public domain, some of it that we found that we developed ourselves. And I think the key ones there, when you pick electricity, is that it has power plant conversion efficiencies. It has correlations for the output temperature of your power plant, which can be used for cogen, for example. And we have some capital cost correlations that is based on what we find in the public domain, such as for ORCs and for flash. The way it works when you pick electricity as end use, there's different approaches and different tools use different things, but the way that we decided to do is it's based on an exergy type calculation, and then it goes from there with a conversion efficiency. So when you pick your subsurface model and you specify all your conditions and you simulate a fluid, you simulate water coming to the surface at a certain temperature and a flow, etc., it actually is very fundamental things that's happening. It just will calculate the amount of exergy that comes out of your well, because that is a thermodynamic property that's really relying on the building libraries that we're using. And I mean, that is just, that will give you the maximum amount of electricity that is that you could generate with a Carnot type efficiency. And that is an output in your metric that is also plotted in your output, or actually it's a metric, it's like an availability, it's called availability within GeoFires, and it's the B here in this correlation. So this is, in a sense, some of the technical background here that's being used, but a lot of people use that approach, do it based on an exergy type calculation. Because this is, the exergy calculation, it doesn't depend, it's agnostic to your surface equipment. It just depends on your ambient temperature, that's your dead state condition, and it depends on the fluid temperature and the fluid flow rate, and in a sense the fluid pressure as well. Because what it will do is, it will calculate the enthalpy that comes up, it calculates the entropy, your naught zero, your zero, that's your dead state, that depends on your ambient temperature, which you do need to specify, and that's why these correlations also are ambient temperature dependent. And your T naught, that's just, you specify your ambient temperature, that's in Kelvin. So as you know, it does not depend on your injection conditions, which I think is, not everybody uses that approach. Some use an approach where you calculate the amount of heat and then use a heat to electricity conversion. We kind of used, I think, maybe a more thermodynamic simple approach. We just use that exergy, and then we have an eta U. This is the conversion efficiency when you pick electricity that you can find correlations in the public domain. We did our own correlations with Aspen Plus for different type of ORC plants and different type of single flash and double flash plants. You do not pick your refrigerant when you pick an ORC. What GeoFires does is it relies on these correlations that were pre-calculated with different type of refrigerants, and it's already picked the best refrigerant for your condition. And this is important because if you have a big drop in production temperature, you may be very off design for your ORC. And right now, GeoFires is not set up yet for dispatchable type operations, for wide swings in temperatures and flow rates and all that, because it assumes it operates at your best condition, and that's perfect for like nominal baseload conditions. We put it in the discussion for later. I think it probably will come up. We've had people ask us about dispatchable geothermal. Could be a nice cool feature, but this is in a sense what it does. And then with this, you can calculate the amount of electricity with correlations like this, and this we've compared this with SAM, and so there's different type of, it's $1 per kilowatt type correlations that are in there. And if you will show a few examples, I'll pick one here. A lot of the ones we showed was already electricity. It's probably one of the most simple ways of running it. All you have to do is you select your end use option to 1. In your surface plant, 1 is electricity. So very simple. You specify, I want to make electricity, and you need to specify a power plant. When you select electricity, only the first 4 are relevant, because the other ones refer to heating applications. You can specify subcritical ORC, supercritical ORC, single flash, double flash. The different correlations will have a different cost associated with them, and have a different exit temperature and a different utilization efficiency associated with them. If you pick a temperature that is outside the range, GeoFires will give you a warning you're outside the range, but it won't crash. It will actually extrapolate. So you're kind of at your own risk at that point. And we've seen some comparisons. Extrapolating a little bit is probably fine. With the ORC, extrapolating too much can get pretty bad, because I've seen some people using an ORC at 400 C, for example, but the correlations were only developed up to 200 C. at that point you're quite off. And we've actually, I think, have an issue even. There is new work that's out there. We may want to build in some new correlations. The same with, for example, different type of power plants. I know what already came up with the like a supercritical CO2 Brayton cycle. That's been, there's a lot of talk about that for high temperature conditions. That maybe is one that should be added to it. Anyway, so this is what's currently being built in, and in this particular case, for example, subcritical RC, that's really all what you need to do, and your ambient temperature, that one will be a metric that's used as well. We want to point out it assumes air-cooled condensers. We don't have the option yet to do a water-cooled based ORC because usually it is air-cooled anyway. I know there's some examples in the world that have a water-cooled ORC. We don't have that capability yet. Those are a little bit more efficient, but the way it does is it subtracts the power for your fans from your gross power. It does that already based on that correlation. So that's always, it has been pre-calculated with, we actually use Aspen Plus, but recently we've done some IPSI Pro calculations as well. So that's the type of, that was some of the modeling that went in there. And all you have to do is if you select that and you run it, it will still calculate your heat. It will provide output for heating. There are results in there that show amount of heat extraction, and I'm kind of like, for example, here this is a system, 95 megawatt thermal. We actually have 3 production wells, so it's a pretty big system. We actually have quite high flow rates. So that's why we get a lot of heat out of the system. So the thermal output, it does get calculated based on your reinjection temperature that you specify. And then with that heat and with those conditions and the temperature, etc., it will calculate utilization efficiency, and it will provide different output metrics for your electricity. It will actually, in the summary of the result, if you pick electricity, it will tell you it's a 7 megawatt average plant. The average is based on the lifetime that you specify. In this particular case, I think we had a quite high lifetime. I saw it was maybe 30 years or so, which is, I guess I can kind of quickly, let's see where I can search for the lifetime. Yeah, we did have a 30-year lifetime. We just have a very gradual decline, which is a very, I guess this example assumed a very, very good reservoir because it doesn't decline too much. Let's see which model we use. Actually, we manually specified the thermal drawdown model. So this case it wasn't really focused on the subsurface, but if we, for example, put a little bit more drawdown on that system, actually, yeah, let's double it, 1% a year. It will, over 30 years, it will go lower, and with that, the power plant output will go down. And you see, we originally were 7 megawatts, now we only get about 6 megawatts. It does have some other metrics. What's your maximum, your total, your initial, etc. So the way it is right now, it just assumes, it takes that decline and it calculates average, min, max. So all those metrics are based on, and they get plotted here as well. These are some of the NPV, but they get summarized in this one. How much electricity are you producing per year? That is as well calculated. What it does is it does so total and net, and the way it does that is it calculates the pumping power that's being required. So it does do an estimation of, it calculates, you need to specify things like well diameter. You can specify injection and injectivity and productivity indices. With that information, it will calculate the pressures along the flow path. How much is being injected? Do we need to do pumping power for the production? It will estimate that. It will calculate the pumping depth, and with that information, it will estimate pumping power. You can have cases where it's 0. If you don't have too much friction, if you have some thermal siphon effect, it will show 0. But in this particular case, we have quite some pumping, and it will calculate gross minus net. And actually, that's actually total is without pumping power. It subtracts the pumping power to go to net. What it doesn't plot here is the power, the auxiliary power within the power plants, because that was calculated as part of the correlations. Things like the fan power for your air-cooled condensers. Unfortunately, we don't have that metric yet to plot here, because that was done as part of ASCOM Plus side. So who knows? Maybe that could be a cool addition if we want to do more detail there, but that's not being plotted here. So as you see, all of this we're doing now, it is actually in the version 3.5, which just was launched today. It does show that at the bottom. But I think this hopefully will show you very quickly how you can run electricity. A lot of the examples are electricity. I can, for example, pick a different one. Example 1 is again electricity, but that's an EGS one. I think we already talked about this one used a multiple parallel fracture. So that's a green garden type system where we specify some conditions on the reservoir. With that, this one actually uses a supercritical ORC. They're a little more expensive to get a little bit better efficiency. This particular example, if people are interested in it, use a very simplified model, fixed charge rate model, etc. So I think if electricity is what you really want to use geophytes for, I think you should really be covered there. I think you're in good hands because a lot of the examples that were created were focused on electricity. And so maybe I'll pause here. Maybe we can take I will take another look at some of the I see there was some in the chat, maybe some additional explanation.
Yeah.
I think by Malcolm as well. So yeah, some of the MPVs. So we've been a lot playing with that. What's your PPA that's required to make electricity, etc. So a lot of that you can play. That's where I think Geophire's tool is really where it can shine to look at these economics and what will take. So that's a good point there. I think we have some extra case studies lined up for support rock, so we're definitely going to get that to that. I feel direct use heat. Maybe we can quickly talk about that because it's lined up with absorption chiller as well, and with the heat pump. All of these are very closely related. So maybe this may be a good time to actually get to that. So I'll share my screen again. Talk a little bit about some of the heating. I'm keeping an eye on the time. We only have about 15 minutes left. However, we have plenty of time we reserved in the afternoon. Whatever we don't get to today, we can talk more about that during the 2 p.m. time slot, talk about more case studies, and really talk about what else you want us to talk about. So let me go back into screen, my monitor, and go back to full screen. We'll keep monitoring the chat here. So as I mentioned earlier, Geophiles originally was about electricity, and that's all been preserved, of course, that capability and expanded. But a lot of the work that has happened as part of the work at Cornell with version 1, as well as afterwards at NREL here, version 3 and beyond, was adding extra of putting a lot of focus on the direct use heating. And it all came from that there was more and more interest on hey, we need so much heat in this country and in the world. A lot of it is low temperature heating, and then it opens it up to large areas in the country as well. So this is a little bit the background. Like we get a lot of this request as well. Like, hey, heating is something we're really interested in now, and how can I use geophiles for that? And so we create additional example files. I have a few highlighted here. I have some, and maybe I'll just go right away to one. Because when you go to heating, you have a few different options you can pick from. Maybe I'll just want to point out, if you want to use heating, you go back to one of the surface plant, the end use option, you set it to heat. I mean, it's very, it's kind of self-explanatory there. So I'm sure all of you were able to use it like that. So you just take end use option heat, and that bypasses the electricity, and it just assumes we're going to use the heat type cost correlations, heat type modules, and the output deck changes as well. So based on your application, etc., it will print out different results and it shows different graphs. So what you do have to do here in this particular example, if you only pick heat and you don't have like an additional application like a heat pump or an absorption chiller, it will assume that all your heat is being used at the surface locally for some application like maybe an industrial process, it could be a greenhouse, it could be even things like fish farming. There's a lot of different low temperature heat applications out there. What we don't have all correlations for each of those ones individually. We have a built-in cost correlation based on the kilowatt. I think it's about $100 per kilowatt or so that we assume, but you can specify your own cost correlation because they vary so much from whether it's some high temperature industrial application at a refinery to snow melt type systems. So you can specify an end-use efficiency factor. What that does is it allows for some losses, thermal losses along the way. Maybe you're not able to use all the heat that's being produced. You may lose some on the heat exchanger. You may use some on the piping or so. All that is a way to reflect that. When you run it like this, the way what GeoPhires will do, it will just show all heat output. It will say we're using heat. Right now it has as default $1 per million BTU as the break-even price. The reason that is historically we often want to compare with the natural gas price, and that is $1 per million BTUs is really like what's really being used there. And that's why that is the output there. But we actually have an example later where we show you how you can change the output unit if you want to have different use. We have one example that shows how to do that. In this particular case, the one we picked, it's a pretty high temperature one. We drill 3 kilometers down. We have 2 injection wells, 2 production wells. A pretty high gradient, 55 degrees C per kilometer, not quite as high as the case study earlier with Fervo, that was 75, but still quite high. And this particular case, you need to specify your reinjection temperature because GeoPhires needs to know, it doesn't know your exact application. If you do something like low temperature heating for homes or even down to, like I mentioned, fish farming, snow melt, those can bring your geothermal fluid temperature really low. If you have an industrial application where you may be using it for some steam process or something, you probably don't get that quite as low. And so it is important that you specify your reinjection temperature. Right here it's 70 degrees, so it's not quite as low as some direct use applications. It's specified right there actually. It's used as information to calculate the amount of heat that's being used. So it still gives you the same reservoir output results. We use a linear heat sweep model. It's another one that's built in. I don't think it's quite used as much anymore. It originates, I think, from Stanford University. They did a lot of work, and maybe it was in the 80s and the 90s where this got documented. It's well documented. All the equations are online. But it's one that can be used maybe more for a hydrothermal type system, but we have a case study that uses that if that's the one that you want to use that you're familiar with. It does need some additional information. You need to specify your porosity, for example. It's one of the metrics that's required, some of the parameters. But if you use heating, similar type of output, it first will tell you how much temperature, but then it will show you how much heating that's being produced. And it has things like net heat put. This one has a little bit of decline with this model. It may go up a little bit. That depends on the Ramey's. That's something we see with the Ramey's model. The Ramey model we use for the wellbore heat losses. We can have quite a lot of losses during the first few months of operation, but once the wellbore has been heated up, you can see the production temperature going up a little bit, and then it starts declining again. So that's a reflection of that. And then it does start going down as well. But it will tell you things like how much heat being generated. And important is if you pick direct use heating, the pumping power is no longer subtracted from your electricity because you're not producing electricity, that becomes an O&M cost. It needs to know your electricity rate for your pumping power. In this case, it still has almost a megawatt of pumping required, and there is a metric. I'm not sure if we quite specified it, but we can just take a look at it quickly. You just type in ELEC, it should come up. I don't see it right away here. Actually, right there, electricity rate. Okay, this is only 5 cents per kilowatt hour. Maybe it's quite low. Maybe it should be 10 cents per kilowatt hour if that's in your application, the electricity rate. Your O&M costs will start going up. You can just rerun it because I didn't look what the original NPV and LQH is, but it uses that metric to calculate it is plotted out here how much pumping power it's part of your O&M cost. In this case, it is quite high, more than $500,000 per year that you are paying for your pumping, and that becomes part of the O&M exercise, and so that's all done in the life cycle cost assessment. So I think that's the more like direct use heat without any absorption chiller, heat pumps, but we have built in that option because we have received that request. Like, what if you use the heat to make cooling? If you want to use that way, we have an example for that. You just pick, it's very simple. You just pick, again, direct use heating. Let's go to this. You pick heating, but you specify it's the same parameter we use. So it's the plant type. Number 5 is an absorption chiller. If you select that as your application for your heating, it will trigger a few things in the background. It actually is already been run here. Let me actually, in this particular example, show you that you can specify a few additional metrics for that. I specified a COP for my absorption chiller, but you can also use a built-in correlation. It uses a built-in correlation for the single effect absorption. It has a correlation there. There is a lot of that is being, again, in the public domain. There's a lot of research, a lot of available material that's out there on costs, on efficiency, etc. for absorption chillers. We try to have the capability to simulate it, but we're not simulating a detailed absorption chiller. It's a little bit a similar approach as with the power plants or with the heat pump. We have a cost correlation for it. We have an O&M correlation for it. We have a performance correlation for it, like a COP. And in this case, I manually provide it, but if I wouldn't manually provide it, it uses actually this one that you'll find some material out there. Let me just go back to it. So an absorption chiller gets specified. I think you can use a correlation. In this particular example, I manually provide that information. Maybe you get a vendor quote or so, or you find that information online. But we can run it first like this. We can put it. We can see we can remove it. But in this case, if you pick absorption chiller, you can notice in the results that you can start seeing cooling things showing up. So it will have converted the heating to cooling with the COP that you provided, and that becomes a new output metric. And in this case, as you know, the conversion from heating to cooling, it's very strongly dependent on the production temperatures that you have. In this case, I think we assumed quite low production temperatures. It's about 100 C that we have. With 100 C, it actually falls about in that range. You may get about 60 to 80% or so heating to cooling. So 10 megawatt of heating, about 7 megawatt of cooling. If you have high temperature cases, you can actually go to COPs above 1. You can get more cooling. So that's being used there. It's an example 11. So maybe I'll. And I know we're running out of time here, but so I just really briefly wanted to go back that another direct use heat application is if you use your heating and you actually want to use it with a heat pump. This is example 10. We I mean, I'll be the first to acknowledge there's so many different configurations. We have limited capability right now, I would say, in geophytes with the heat pump module, because there's different ways of coupling your geothermal fluid to the heat pump, to the secondary fluid that you're going to be heating up. Like, how is that all being integrated? Have you multiple in series, for example? There's a lot of research. Some of it actually we're looking at also. That was part of the district heating project I talked earlier about at Cornell. There's heat pump is one of the configurations there that we've looked at. If you select the heat pump one, it has correlations, a capital cost correlation as $1 per kilowatt. Let me just open it up quickly. And it does assume the heating gets then boosted up with a COP that is user provided, and then you have additional heating that you can get. So right now, that is the assumption that's being made. It's really to boost the heat that you get. But you get a lot of electricity consumption as well. And if you run the heat pump module, you will see that additional, maybe I'll just go here quickly, for example, of which heat pump cost. Because you selected heat pump, there is an additional heat pump cost that's based on your thermal application, like the size of the application. It also will calculate how much electricity that you need for your heat pump, and that becomes part of the O&M cost. And so you need to specify an electricity rate, similar as we earlier mentioned. This case, we had 7 cents per kilowatt hour. We did specify heat pump capital cost in there. And so I specified a COP as well in there, and so that's the way that module works. So this is just
a quick question on that. Can you, if you can hear me, can you speak to the depth constraints then that you alluded to about the heat pump and limitations around shallower versus deeper heat pumps?
Yeah, that's a good point. So right now, the way it's set up is actually it uses the heat pump only for heating. So it will require a little bit of changes to go from heating to cooling. But like, I think here is where the linkage with shallow geothermal may come in. Right now it assumes a deep geothermal type system where you can make it, you could do a hot spring type system where you could say, like, the hot water is available at the surface. You have that capability, but it doesn't have a reservoir model for borehole thermal energy, like G-function type systems, a borehole field. It doesn't have that reservoir model at this point. But that's probably where that will need to be built in, and then linked to a heat pump where you let the COP be a function of the production temperature, and probably do an hourly simulation instead of the way what I just showed you was it's one with a gradual decline in production temperature. And we only have, you can choose your time step, but in a lot of the cases, things don't change on an hourly basis. We just have it as set up as maybe a few time steps per year, except for the district heating. There you do want to have it an hourly or a daily, because there things can change much more rapidly. But that's a good point. I think the heat pump module is where the shallow geothermal probably could come in if you want to ever build in a GEG designer type tool or something like that, another module.
Can you speak to how the reservoir model in this case though, and like how that's structured? And somewhere in the literature, I cannot remember where, I remember seeing some 5,000 foot or deeper sort of depth constraint. I don't know if I can't find that in the documentation, but can you speak to sort of the configuration here?
Yes, with the heat pump one, we assumed in this particular example, it's a 2 kilometer deep system that we specified. So this is a deep geothermal that gives us hot fluid that we try to boost even more, try to get even more heat out of it by coupling it with the heat pump. That was an approach that was done here, and we've definitely seen some district heating. There's some examples already. Like I believe the one in Paris it's a common scenario where they have hot fluid coupled with a heat pump. It provides some more heat. It provides some additional flexibility. It touches a little bit about peaking heating. What if suddenly on a cold winter day that heat pump can really kick in there? So that's the type of applications that we focused on. But the depth you choose can really be, you can go to really high. We don't have an upper limit here really, and and the lower limit can be quite low, but it just won't assume a borehole thermal energy type calculation, a borehole heat exchanger type calculation. And
this is our
yes.
We do have to do a room change here. Thank you everyone so much for your response.